Hello everyone, and welcome back to the channel. Today, we're diving into one of the most exciting and frankly, mind-bending topics in space exploration. How exactly will SpaceX land its colossal Starship on other worlds? We've all seen the incredible animations, but the real-world engineering challenges are immense. And some recent comments from SpaceX have thrown a fascinating new possibility into the mix. Let's start with Mars. During a recent presentation, SpaceX's Senior Director of Starship Human Landing System, Dan Witt, dropped a bit of a bombshell. He discussed the idea of landing Starship on the Martian surface without any landing legs at all. Now, take a moment to process that. A 120-meter-tall rocket, the most powerful ever built, just setting itself down on its own base. Witt suggested they could land directly on the skirt, which is the flared section at the bottom of the vehicle that houses the engines. This would be a truly minimalist approach, shedding a huge amount of weight and complexity. If you don't need legs, you don't need the mechanisms to deploy them, you don't need the extra mass, and you remove several potential points of failure. The idea is that Mars, with its relatively flat plains and many landing zones, might be forgiving enough for this audacious maneuver. You'd essentially be relying on the rocket's own structure to act as its landing pad. It's a bold concept, but with SpaceX, bold is just another Tuesday. This radical idea for Mars immediately begs the question, could the same be done on the Moon? Well, this is where things get a lot more complicated. The current plan for the lunar Starship, the one NASA has contracted for the Artemis missions, absolutely includes landing legs, and for good reason. Unlike the vast, smooth plains of Mars, the lunar surface, especially in the polar regions where we want to go for water ice, is a minefield of craters, boulders, and steep slopes. The terrain is incredibly uneven. A flat, circular skirt just isn't going to cut it when you might be landing on a 10-degree slope or straddling a small crater. You need the articulation and adaptability that landing legs provide to find stable footing and keep the towering vehicle from tipping over. So for the Moon, legs seem non-negotiable. But that brings us to the next massive challenge: the legs themselves. Starship is a beast. Its dry mass alone is estimated to be over 100 metric tons. When you're landing that much weight, you need some seriously robust legs. We're not talking about the spindly legs of the Apollo lunar module. The engineering required to design, build, and test legs that can support a skyscraper-sized rocket, absorb the impact of landing, and keep it stable on a treacherous surface is a monumental task. Early concepts showed Starship with 3 legs, similar to the Falcon 9 boosters. But as the design has matured, it's become clear that 3 probably won't be enough. The stability just isn't there for a vehicle this tall and heavy. Later renders and expert analysis suggest it will need at least 6 landing legs to create a wide, stable base. Think of it like a tripod versus a 6-legged stool. The more points of contact you have, the more stable your structure is, especially on uneven ground. Each of these 6 legs would need to be incredibly strong, yet as light as possible, and feature a complex deployment mechanism. It adds a significant amount of mass and complexity back into the system, which is precisely what the legless Mars concept tries to avoid. Now, let's get into a bit of the physics behind this. It's easy to think that because the Moon has only 1/6 of Earth's gravity, everything is easier. Tipping over should be harder, right? Well, yes and no. The fundamental physics of stability, specifically the angle at which an object will tip over, is determined by its center of mass and the width of its base. This maximum tilt angle is actually the same on the Moon as it is on Earth. If your center of mass moves horizontally, beyond your base of support, you're going down, regardless of gravity. However, the dynamics of getting to that tipping point are very different. Lower gravity means that any forces acting on the rocket, like the final touchdown impulse or a slight shift in propellant, will result in slower, more drawn-out movements. It's like watching something fall in slow motion. This might give the reaction control thrusters more time to correct any instability. But it also means that the initial landing itself is incredibly tricky. You have to kill your velocity perfectly. If you come in with even a small amount of horizontal motion, the low gravity and lack of atmospheric drag mean you could easily slide or skid across the surface before the legs can get a firm grip. And once you start to tip, even if it happens slowly, the immense scale of Starship means the top of the rocket will be moving a significant distance. The forces involved in stopping that slow, massive tip would be enormous. This brings us to the core concern that keeps many engineers up at night. Starship's inherent stability or potential lack thereof. It's an incredibly tall and slender vehicle. We'll be talking about a height-to-width ratio that is far more extreme than anything we've ever tried to land. Its center of mass is very high, especially when it's nearly empty of propellant after landing. A high center of mass makes an object much easier to tip over. Think about trying to balance a pencil on its tip versus on its eraser. Starship is the pencil on its tip. Every single aspect of the landing sequence has to be perfect. The landing site must be surveyed to a ridiculously high resolution to ensure there are no hidden slopes or rocks. The guidance and control systems have to be flawless, bringing the rocket to a near-perfect zero velocity at the exact right altitude. The landing legs must deploy reliably and absorb the final impact without bouncing or shifting. Even after a successful landing, the risk isn't over. Could a moonquake or a micrometeorite impact be enough to destabilize it? Could astronauts moving around inside or cargo being unloaded shift the center of mass enough to cause a problem? These are the questions that SpaceX and NASA are working tirelessly to answer. So we have two very different worlds requiring two very different solutions. For Mars, the tantalizing prospect of a super-streamlined, legless landing that leverages the planet's smoother terrain. For the Moon, a more traditional but incredibly challenging engineering problem of creating a robust, multi-legged system to conquer its rugged landscape. The sheer height and high center of mass of Starship remain the primary concern for both scenarios. Successfully landing this vehicle on another world will be one of the greatest engineering achievements in human history, pushing the boundaries of what we thought was possible. It's a nail-biting, thrilling challenge, and we'll be watching every step of the way. What do you all think? Is the legless Mars landing brilliant or crazy? Do you think the six-legged lunar Starship is up to the task? Let me know your thoughts in the comments below. It's always great to hear your perspectives on these incredible engineering puzzles. Thanks so much for watching today. If you enjoyed this deep dive, please consider hitting that like button and subscribing to the channel for more content on the future of space exploration. We'll see you in the next one.